All right, well, good morning and welcome to those here in person and online. My name is Christina Anastasi and I am a branch head in the Minerals, Energy and Groundwater Division here at Geoscience Australia. I have the pleasure of being your chair for today's Public Talk seminar. Before we begin, I would like to personally and for Geoscience Australia acknowledge the traditional owners and custodians of country throughout Australia and acknowledge their continuing connection to land, waters, sky and community. We pay our respects to the people, the cultures and the elders past and present and any traditional owners joining us here today. Now, today you're actually going to learn what are critical minerals and why they matter. This session will be presented to you by two senior and respected officials from Geoscience Australia, Karol Charnotta and Allison Britt. Now, Karol, he is the Principal Science Advisor for Mineral, Energy and Groundwater at Geoscience Australia, providing strategic advice and shaping science direction. He was instrumental in directing the science focus of the successful Exploring for the Future program and is today driving the strategic science and its integration in our newly funded government pre-competitive geoscience initiative, Resourcing Australia's Prosperity. Karol has over 20 years of experience in undertaking and leading pre-competitive geoscience programs that are focused on understanding Australia's geology and its resource potential. Now, for those of us who know and work with him, we can all confidently say he is passionate about his work and delivering impactful earth science for stakeholders. Allison, who will be joining Karol, leads the provision of technical advice on mineral resources to the Australian Government, supporting the development and delivery of government policy resource agendas. She is a strong advocate and promoter of the value and benefit of government pre-competitive geoscience to Australia, including providing us with a comparative advantage for new investment in our resources sector and supporting new and emerging and strategic opportunities, including critical minerals. Allison's drive and passion and ability to translate complicated science jargon to everyday government policy speak, coupled with her understanding of the minerals industry development life cycle, always amazes me and has made her a great and known advocate of Geoscience Australia and Australia's mineral industry. Please join me in welcoming Karol and Allison to the stage. Thank you.
All right, thank you very much for the introduction, Christina. Very kind words there. Last Friday, Donald Trump signed an executive order for the US to immediately ramp up mineral production on federal lands with known mineral resources. He made this the priority for those lands. Last year, China banned the export of antimony to the USA. This is joining export bans on gallium, germanium, graphite, and some rare earth technologies. And the EU signed into existence a Critical Raw Materials Act. What is going on? So the control of critical minerals is behind these actions. And today, Karol and I are going to explain what critical minerals are and why they matter. A bit of a 101. You'll hear more about the USA and China and some other nations, but mainly we're going to try and provide you with an Australian perspective on these things so that you can understand the headlines you're seeing, how they affect Australia, and the extraordinary opportunity that we have to leverage Australia's natural minerals endowment. We also want you to have an appreciation of the really important role that we as government geoscientists play in creating new critical mineral supply chains, as well as the impact that our science has on ensuring that we have those pipelines for the future. Now, Christina's already done this, but to start, we wanted to acknowledge that our critical minerals are found on the countries of our First Nations people, our first miners, mappers and navigators. And so we too pay our respects to elders past, present, and any First Nations people here today. So who are we to be explaining critical minerals to you? Well, inspired by our Chief Scientist talk last week, when he spoke about all of us as geoscientists, we thought we'd start by telling you a little bit about ourselves and our motivation for today's talk. So I'm Allison Britt, GA's Director for Mineral Resources Advice and Promotion. I've got some 30 years mineral experience in gold geochemistry, regolith research, uranium, mine waste, fieldwork around Australia and in Patagonia, which is the site of my one and only geophysical survey. For the past 15 years, I've specialised in Australia's minerals inventory, and as critical minerals have become more and more topical, I've been increasingly called on to communicate about them, and it's been a great privilege to be able to do this to a wider audience through ABC Landline, ABC Four Corners, for example. The other part of my job is promoting Australia's competitive advantages, including its world-leading government geoscience, so that we can attract that international investment that we need to develop Australia's mineral sector. So the photo in the middle shows myself and Karol, along with Steve Hill, Marina Costello and Michelle Cooper, spruiking Australia's credentials at the world's largest resources conference in Toronto just a few weeks ago.
So throughout this talk, Alison and I are going to kind of share the podium. So hopefully that makes it a little bit more interesting, more dynamic for you. First, a little bit about me. So I started Geoscience Australia over 20 years ago as a graduate. My role was to do field mapping, looking at structural overprinting relationships, Australia's resource potential for deposits. So there I am over there, entering data in the evening after lots of traverses in the Patterson. Then I went off and did a master's in petroleum geoscience and tectonics, and after that a PhD at Cambridge University in geodynamics. So it's the quantitative understanding of the processes that shape our planet, so to speak. When I came back, became the Director of Mineral Potential, and for the last 5 years have been providing science advice to the large, I suppose, resource programs at Geoscience Australia. Now, last year in December, Alison and I published a paper. It was solicited to the Australian Journal of Earth Science Special Issue on critical minerals. We were provided a review of critical mineral resources in Australia. So the majority of the material in this particular talk has been drawn from there, so I encourage you, if you're interested, to go and look into this. And we've also, it has been shaped by contributions to a critical minerals course at the Australian National University. So in our presentation today, what we aim to do is to first cover why do criticals matter, then what are critical minerals and strategic materials, what is Australia's critical minerals endowment in a global context, and last, how is Australia growing its critical minerals sector, specifically through geoscience? So Alison, why do criticals matter?
Okay, so let's start with the mobile phone as an example. You've all got one of these. It's an example of how we're using a wider range of minerals than ever before in history. But have you ever wondered what exactly is your mobile phone made of? Well, in 2019, some researchers from the University of Plymouth decided to find out. And they did this by sticking a phone in a blender. So, yep, you heard that correctly. They stuck the phone in the blender, turned it on. Please do not try this at home. So, what did they find out? Well, the phone's mostly made of those everyday elements, the ones that we'd expect, iron, silicon, copper, nickel, aluminium. But the phone also had small amounts of lots of other elements: tungsten, tin, rare earths, silver, cobalt, moly, gold, tantalum, and tiny amounts of niobium, antimony, germanium, and indium. And this is important because each of those elements, used in small amounts, is what makes our modern technologies work. So just like adding salt and pepper will make your meal taste better, a little bit of critical minerals will do the same thing. So adding rhenium to a jet engine makes it burn hotter and faster. Adding a little scandium to an aeroplane makes it lighter and stronger. And adding indium to your mobile phone will make the touchscreen work. But those elements are not always easy to get. And so we're seeing around the world increased competition for mineral resources playing out. We're seeing three main themes at the moment, comprising energy security, economic sovereignty and capability, and defence supply and resilience. I like to think of it as the three E's: energy, economy, and existence. Now, these are global drivers, but Australia's also impacted. And you can see the resultant policy responses from the Australian government in the examples on the slide. We have a net zero by 2050 target to ensure that we have sufficient energy capabilities as we decarbonise our economy to meet our Paris climate change commitments. We have a Future Made in Australia Act to grow our economy, including downstream value adding in our critical minerals sector. And we're part of the AUKUS trilateral security arrangement, which is an example of increased national security concerns by Australia and our strategic partners. All of these things require critical minerals.
To emphasise the point Allison is making, it seems not a week goes by without some headline about critical minerals resources and the race to secure them. Concentrated markets, a rise in demand and shaping geopolitics, competition and anti-competitive behaviour is rising, and geology has never been the centre of attention, especially for minerals, in my entire career. It's an amazing time to be in this particular space. So let's unpack these drivers a little bit more. Allison talked about the secret spices and ingredients for a mobile phone, which contribute small volumes to a mobile phone. But there are also other technologies which drive huge demand for critical minerals and strategic materials. One of these are cars. So electric vehicles require about a fourfold increase of critical minerals and strategic materials than the conventional combustion engine. You can see that as the growing population around the world transitions to technologies like these, that demand for this is going to ramp up significantly. There are companies, there are agencies who spend a lot of time forecasting what the future will look like. A key to all this is the International Energy Agency. It's at the heart of the global dialogue on energy provision and providing authoritative analysis, data and policy recommendations that periodically release forecasts. Here you can see the minerals for the net zero transition, what was used in 2023, and three scenarios. One is the STEP scenarios, there's the stated policies. These are things that have been legislated, and it's kind of like the most conservative estimate of what the demand is going to look like. Then you've got the announced pledges. So these are things which haven't quite made it into legislation. And then you've got the view from the International Agency of how much resources are actually going to be required to meet net zero. It's interesting to note that the increases that we're seeing here are generally between 2- and 3-fold and sometimes quadrupling by 2050. That's incredible. The resources industry estimates that investments of about $100 billion per annum are going to be required until 2050 to reach net zero. That's a huge opportunity for a resource country like Australia. These forecasts also often reach headlines in newspapers because they are big, they're grand, and there is sometimes some cynicism. Is it really going to be that big? What a lot of people don't realise is that we've actually been undergoing this transition already. So if you take annual production of these various critical minerals and strategic materials and you benchmark it to the turn of the century and then present it like this to look at the forecast growth, you'll see that we've been increasing our production from 54% for graphite to a whopping 975% for lithium. That's staggering. And Australia has played a key part in this. We've gone from zero to hero in lithium production in just 8 years, reaching #1 global producer in 2016, 2017. So the opportunities are very, very large. But do we have enough resources in order to be able to sustain this type of growth? So back to the International Energy Agency forecasts again. What you can do is you can take all of those, add them up cumulatively out to 2050, and compare them to all of the economically demonstrated resources that Allison's team and others at the United States Geological Surveys compile. And what we find is that we don't have enough resources yet out to 2050. There are shortages of a few percent for copper to tens of percent for cobalt, but please notice the y-axis changes on these graphs. We are short by hundreds of millions of tonnes for copper and 1 or 2 orders less for elements such as cobalt. And these numbers are most likely underestimates, because it's unrealistic to think that all of the previous discovered resources are actually going to be developed. There are other things that stop resource development, such as environmental and social issues. A lot of these resources are going to be, I suppose, added to the global inventory through drill outs of brownfield exploration. But greenfield discoveries are also needed. And what's important here is that it normally takes about 17 years from discovery to development of a deposit. So in other words, to meet these shortfalls, we need to be acting now. We need to be exploring and looking for the future deposits now. But the challenge is even greater than that. It's not just about extraction of resources. Yes, those extraction activities can be very focused in certain countries, like, for example, graphite and rare earth elements in China, lithium in Australia, copper in Chile. But it's also, where do we process and make the final products for these that to be used in the technologies that are driving demand? And in this, China dominates the race at the moment. So the key for a healthy economy and greater geopolitical stability is actually to be looking both at the extractive component and also going downstream and diversifying production.
So, hopefully we've grabbed your attention with that, and you've all got the general idea that critical minerals are in hot demand. But which minerals exactly are we talking about? So, the generally accepted definition used around the world is that critical minerals are elements or minerals that are essential for the functioning of our modern technologies, economies, or national security, and have supply chains at risk. That "and" is important. Now, the concept of critical and strategic minerals isn't a new one. Throughout history, certain mineral commodities have been of immense value, contributing to the rise of various societies. For example, salt exploitation led to the first European town in Bulgaria nearly 7,000 years ago. Iron ore resources from northern Italy and conquered regions supported the Roman Empire. And the British Empire expanded its might on the back of its copper, coke and coal and iron ore resources. So mineral resources and access to them have always played a significant part in the fortunes of civilisations. Now, more recently, the upheavals of the 20th and 21st centuries have resulted in many nations seeking to define the occurrence and availability of critical and strategic minerals, with the United States of America leading much of the thinking and action in this area. So we'll start with World War I, where the Americans first used the term war minerals, followed by the first official list in 1921. Now, if it bothers you that we use the term critical minerals when we're talking about elements, then you would have hated the war minerals list. It listed only 20 of the 42 commodities were actually minerals. So, it included things like goose feathers. So the point I would make here, So the point I'd make here is that the critical minerals is rather a political term rather than a scientific one. Now, in 1922, the US defined strategic minerals as those necessary to the prosecution of war, but with insufficient domestic supply. And in 1932, they introduced the term critical minerals, as they recognised that some minerals were easier to get than others, say from their dear neighbours to the north. In this case, critical minerals were less vulnerable than strategic minerals, which is a reversal of the current terminology, which we'll get to. Now, in 1939, the US also coined the term essential minerals, recognising that some minerals were crucial to the economy but had no supply issues. But by 1944, in the midst of World War II, the US had stopped making these distinctions. The war experience had shown that the difference between strategic and critical was largely academic. So what was happening in Australia? Well, World War II highlighted the need to establish an Australian inventory of strategic resources. And from this, the Mineral Resources Survey and the Minerals Production Directorate were born. After various mergers and name changes, we know it today as Geoscience Australia. And this work continues, led by our fantastic Mineral Resources Advice and Promotion team. Now, fast forward to the 1980s, and the Strategic Minerals Inventory Group, comprising US, Canada, South Africa, Germany, the UK, and Australia, was established to cooperatively gather information about major sources of raw materials, but it struggled to find a mutually acceptable definition for strategic minerals and critical minerals. And so it was recognised that these terms were coloured by each nation's perception of vulnerability. By 2006, the Spanish Geological Survey had proposed definitions for critical and strategic minerals that were broadly accepted, with strategic minerals being critical minerals, but the ones used for military purposes. And in 2013, Geoscience Australia published its landmark report, the Roger Skiro et al. Critical Commodities for a High-Tech World, that essentially helped position Australia's policy response when the first Trump administration issued an executive order tasking the USGS and the Department of Defence with determining the minerals vital to US interests. Now, the result of that executive order was the first modern US list of critical minerals, which comprised 35 commodities at the time, released in early 2019. Now, I'm calling it a modern list because it utilised new approaches in government for measuring mineral criticality. Essentially, the approach was to plot the two main requirements for mineral criticality, that essentialness on one axis and that vulnerability on the other, and see where the commodity lands. But how are these measurements made? I'm now going to hand you back to Karol for a mini maths lesson.
Thanks, Alison. Look, last week we had a talk from Steve Hill talking about geoscientists. And he kind of defined science and emphasised a component of it. Yes, it is about the knowledge that we gain from it, the information, but it's also about the process in which we get there. So we want that to be transparent, we want it to be robust, we want it to be repeatable, all these good things. I'm also, in my mind, I've got my PhD supervisor who said it's always useful to show one equation in a talk. So here we go. So Geoscience Australia does have a method of calculating criticality and quantifying, but it's not public yet. So in order to give you the flavour of what goes into criticality assessments, in particular what type of information is used, I'm going to go through the USGS methodology here. Their view is really from a supply perspective. They have a very large manufacturing sector, and they're concerned about where are they going to source the various critical raw materials from in order to make that work. They can reduce this whole criticality, score into one number, supply risk, but it's a function of three for them: the disruption potential, trade exposure, and economic vulnerability. So let's go through these one by one. The disruption potential is really focused on understanding what is the potential of a country who's producing it to supply it to the United States in this particular case. So it looks at that country's share of the global production, and then it's a function of that country's ability to supply it. And here they go into social science, things like the Fraser Institute surveys in terms of how well do companies think they can operate within those countries in order to supply resources from it, as well as that country's willingness to supply, which they then find proxies for in terms of what are the amount of trade ties they have, how common are their shared values, and also how many military ties and cooperations do they have. Then moving on to another component, the trade exposure. So this is largely done using trade data that is collected at ports of entry and departure. So this is looking at the total imports and total exports. So this is where we will go to the shipping kind of lanes and look at their books, as well as the stockpiles. Now, the United States has a stockpile of critical minerals and strategic materials. I think they're kind of eating into it a little bit and they want to expand it again. I know other countries, such as China, have stockpiles and they're growing them at the moment. And we also know that some companies, even companies in Australia, have stockpiles of certain types of critical minerals. And then they effectively look at that with respect to the apparent consumption. So what is the primary production within the country, so the mining itself, as well as how much is being recycled. And they have numbers for that too, which is rather remarkable. And the last factor is economic vulnerability. So this draws predominantly on data from the Bureau of Statistics or their equivalent in the United States. So this is what is the industry's value add as a function of gross domestic product multiplied by the industry's expenditure on that component, on that commodity as a function of the industry's operating profit. What this means is that if you spend very little on a certain critical mineral and you have a large operating profit, you can probably stomach a large rise in the cost of that particular critical mineral and it won't make a material difference to that particular industry. But if it's the other way around, you're in big trouble, so to speak. So by quantifying it, they can then track how criticality changes through time. It's not constant. That's why various lists get updated on a periodic basis in most countries. So here is an example of yttrium. Yttrium, you can view it as grouped in with the rare earth elements. It's associated with them. And at that time, they weren't tracking the rare earth elements. So in 2008, 2009, things were kind of moderate. By 2011, China's share of rare earth elements exceeded 95% of world production. And in that year, they then put a restriction on exports of rare earth elements, cut them by 40%. It's known as the rare earth element crisis. You can see that there's a nice expression there in 2011 as the criticality kind of score increases at that particular point in time. In 2012, the US with the European Union, Japan, took China to the World Trade Organization and lodged a complaint around all, and with time that was resolved in a sense. And you can see how the criticality kind of score decreases. That event itself also created a flurry of activity among industry, academia and government looking for alternative rare earth element supplies, substitutions to other components, and that's why the criticality score changes also. Amazing innovation was done then, but as soon as the market went back to where it was previously, a lot of those innovations were mothballed to be looked at a future time. So it kind of demonstrates the various challenges that we have in terms of how to act during various phases of this criticality, I suppose, challenge.
Okay, thanks. So now that we've learned, we've had the maths lesson and learned about how some countries define and assess critical minerals, what about Australia? So we take a slightly different approach because there is a major difference between us and countries like the USA, the UK, the EU, Japan, Korea, etc. And that big difference is that we are an export nation. Other countries have assessed their mineral criticality on their import and manufacturing vulnerabilities, whereas we're a mining superpower and we export far more than we use at home. So with that in mind, Australia defines critical minerals using that common definition of the commodity being essential for modern technologies, economy, national security, with supply chains at risk. But to be on Australia's critical minerals list, the commodity must also have moderate to high geological potential, and it must be in demand from our strategic partners. We have an outward focus when assessing criticality. We also define strategic materials, but unlike historical definitions relating to military use, strategic materials are now related to modern priority technologies. And the main difference between strategic and critical in this case is that strategic material supply chains are not currently considered at risk, although they'll be watched closely. So let's take a look at Australia's list. So the Australian Critical Minerals List comprises 31 commodities, and you can see the 5 strategic materials in the grey down the right-hand side. It's not showing up very well with the lights, I'm afraid. But you'll note that all the minerals listed have either moderate or high geological potential in line with that official definition. And the slide also shows that Australia currently produces 16 of the 31 critical minerals and all 5 of the strategic materials. Now, despite Australia's different approach to determining mineral criticality, there's still many commonalities across the different national critical mineral lists. So here we've synthesised the critical mineral lists of Australia and 8 like-minded partners listed in the heading and used the periodic table for visualisation. There are 118 elements on the periodic table, of which 79 are mined from the solid earth. We've coloured the periodic table from light to dark, according to the frequency of the commodity being included on the lists. So the dark colours are the more frequent. So combined, 65 elements are regarded as critical minerals, and of these, 32 elements are only produced as co- or byproducts. The slide shows that 17 elements are universally regarded as critical minerals, including antimony, cobalt, gallium, graphite, lithium, tungsten, platinum and palladium, and some of the rare earth elements. At the other end of the scale, unique interests can be seen with the selection of uranium by Canada, coking coal by the EU, cadmium by India, lead by Korea, thallium by Japan, and high purity alumina by Australia. So to sum up, I'd say that despite these different concepts of critical and strategic minerals and those changes over time, the one constant is the need for comprehensive, accurate and timely minerals information. So now that we've defined critical minerals and strategic materials and talked about that growing demand, let's take a look at the Australian endowment and potential in the global context.
So starting with the global context, here you can see the size of the minerals market in terms of annual production. I should stress that the y-axis here is a logarithmic scale. So each horizontal line that you kind of see on there, the amount of production increases tenfold, which is significantly important to understand. The tonnage of, you can see kind of the high tonnage component here is iron oxide, bauxite, chromite. These are kind of construction alloy kind of elements. Then there's phosphate and potash, which are fertilizers. On the other end of the end here, we've got iridium, rhodium, ruthenium, and so on. A lot of platinum group elements. The colours on this graph show whether it's a critical mineral, a strategic material, or other mineral. You can see that the other and the strategic materials are clustered towards the high tonnage end of this particular graph. That's because in those places we have a lot of different mines contributing to the supply chain around the world. Whereas on the right-hand side, we have more of the critical minerals clustering. So these are low tonnage operations. Some of them don't even reach 10 tonnes a year in global production. The volume that is mined, I think, is super important to get our heads around, and this visual, I think, is fantastic at communicating it. In terms of volume of production, there is more iron ore mined annually than all of the other commodities put together. That is remarkable. 2.6 billion tonnes. We've been so ingenious to actually get this industry up and going. Australia is really at the heart of it, supplying 40% of the world's production in iron ore. We've come up with monster trucks to be able to do this. We've got one truck can take 363 tonnes in one go. Yet even using those trucks, you'd still need 7 million trips in order to just ship the ore, let alone the waste in these operations. Phenomenal logistics. Yet on the other end of the spectrum, platinum group elements, you could fit them just about all in just one of those trucks. So this is the challenge in critical minerals. How do you establish yourself as a significant player in these types of markets with low volumes? Another way to understand the market itself is to look at the value that is generated from this. So you take the tonnage and you multiply it by the value per tonne, and this is what you get. So again, what we see here is that the other and strategic materials generally cluster towards that high value end, and this is where a lot of the kind of very large mining companies operate, and the critical minerals tend to cluster at the other end. But there are significant movers on this list. So if you take, for example, some of the rare earth elements, so rhodium, for example, is gone from right on the right-hand side right up to the top quarter of this particular graph. So even though it's low volume, the value can be very, very significant. So how does Australia compare to this? Where is Australia's mining wealth coming from? These are the top, I suppose, commodity earners for Australia. you can see that the majority of them are in this other and strategic materials category. There is lithium and nickel that fall into critical minerals. In 2023, it's likely that the lithium value is slightly overinflated because the price was very high that particular year, so kind of slide back down. So the question arises, can the critical minerals sector have a materially significant contribution to the Australian mining industry or not? So one thing that you can do is you can run a thought experiment. We can go back to the International Energy Agency and look at their forecasts for growth. They released one in 2022 looking out to 2024. On the left-hand column over here, you can see the forecast growth of these particular commodities. In the middle column, you can see Australia's resource ranking. So how much of this do we have? And we're pretty well positioned for a lot of these commodities. On the right-hand column, you can see what was our income from those commodities in 2022. So if we just do the obvious thing, is just to say, what if Australia maintained its market share? We're not seeking to grow, we're not seeking to decrease, but just maintaining that particular share. And these are the numbers that you get in 2024. The total is valued at 196 billion. That's 170 billion more than in 2022. And just for comparison, Australia's coal industry that year was worth 127 billion and thermal coal 62 billion. In other words, it does seem as if critical minerals can make a material difference to Australia's economy into the future because of the forecast increase in demand going forward.
All right, so keeping going with that topic, I think most people here are probably familiar with the major contribution that the resources sector makes to the Australian economy. So Australia currently produces 27 major and minor commodities from more than 300 mines. We're the world's largest producer of iron ore, bauxite, rutile and mined lithium, and a top 5 producer of zircon, cobalt, manganese ore, tantalum, rare earths and zinc. In the last financial year, the mining sector contributed more than 11% to GDP and provided 65% of our export income. The mining sector also employed 300,000 people and indirectly employed 1 million more. So understanding what minerals are already available or identified is absolutely essential for seizing those economic opportunities that Karol was talking about. You can't improve what you don't measure. So each year, Geoscience Australia publishes an assessment of the nation's minerals inventory in our flagship report, Australia's Identified Mineral Resources. The latest version came out a few months ago. It uses 2023 data because 2024 is not yet available. Highlights from the report include increased resources for 13 of the critical minerals, and this includes vanadium, up 18%, now placing us number 1 in the world. We also saw major increases in PGEs, manganese, graphite, lithium and niobium. And on the slide, I've shown some of the significant changes in critical mineral production in 2023, with moly, rare earths, tungsten and others seeing noteworthy increases, albeit some are from a very low base. So how do we know how many resources we have? How do you trust these numbers? So as part of our governance structures in Australia, publicly listed companies are required to report their ore reserves and mineral resource estimates to the Australian Securities Exchange. Since 1989, they've done this using the Australia's Mineral Resources Reporting Code, which is known as the JORC Code. Now, the JORC Code operates under the principles of transparency, materiality and competency, and it's actually part of the listing rules for the ASX. Now, the diagram shows the classifications with the highest geological and economic confidence. If you look at them, the highest ones are the ore reserves. And these are derived from measured and indicated mineral resources, what we would refer to as demonstrated resources. They provide a relatively short-term outlook on what can be produced according to the mine plan. Now, at Geoscience Australia, we use the national classification system. It predates the JORC Code. And it also includes sub-economic categories, which are important for governments to know about, but by definition have no place in a commercial reporting scheme. The category with the highest economic and geological confidence in the government system is Economic Demonstrated Resources, or EDR for short. EDR is made up of those measured and indicated resources that support mining planning, and it's inclusive of ore reserve. It provides a way for government to understand our long-term potential for mineral supply. So the latest numbers reflect Australia's extraordinary resources wealth. That hasn't changed. Australia dominates global resources for a large number of critical minerals, including almost 80% of the world's zircon, 70% of the world's rutile, and 50% of the world's vanadium. We have smaller but still significant quantities of traditional energy minerals like coal and uranium, but also battery minerals, nickel, cobalt, manganese, and of course lithium. As mentioned earlier, we're the world's #1 producer for mined lithium, but we now also produce refined lithium hydroxide. And I won't repeat the production stats from a couple of slides ago, but I'll have you note that our production performance is not quite on par with our resources potential. And later in the talk, Karol will show you an intriguing slide about which mineral deposits are the most rapidly developed and which languish unloved. I think it's also fascinating to compare the profile of established mineral industries with critical minerals using EDR as a proxy for the developmental maturity of the sectors. So here you can see the proportions of EDR for major minerals attributed to operating mines in green, mines on care and maintenance in red, developing mines in yellow, and the undeveloped deposits in blue. And you can see that the graph's mostly green, showing that operating mines account for the bulk of EDR for most of these commodities, and the hatching showing ore reserve also associated with the operating mines for the most part. Now, compare that to the critical minerals for which we have EDR. The colours are all over the place, and this reflects the different stages of maturity for each critical minerals market. So, for example, lithium and associated tantalum, EDR, that's nearly all green and yellow. So it's attributed to operating and developing mines with scarcely any resources in the blue, showing undeveloped. And this is reflecting just how hot the lithium sector has been over the last decade. On the other side of the coin, you can see vanadium, fluorite, rhenium resources. They're mostly blue, they're undeveloped. And this, and hafnium is yellow. It's only one stage only one mine in development. And so what we've got here is essentially a snapshot of a fledgling market sector. And you can also see this market immaturity reflected in our annual critical minerals map, which shows that we have 499 deposits with a critical mineral resource, but only three-quarters of the 499, but three-quarters of the 499 have not yet been developed. We've got 47 operating mines producing critical minerals with another 30 in development. And the figurative Indonesian earthquakes that hit the nickel industry last year, along with those sky-high nickel prices returning, sky-high lithium prices returning back to their long-term base, that's resulted in a large number of mines being placed on care and maintenance in 2024. So we've got 41 mines on care and maintenance last year compared to only 23 the year before. So clearly there's some barriers, but also opportunities when it comes to utilising our known resources to further develop our critical minerals sector.
Okay, so up until this point, you could be excused to think that, oh, well, if we needed some more gallium or germanium or indium or any of these kind of elements, we could just go out there and start a mine to get these commodities out. But the reality is actually much more complicated. Allison alluded to it on the slide of the periodic table that 32 of the elements are only produced as co- or byproducts of the mining of other minerals. So, and that's a really important point, that there are associations between different styles of minerals. In the centre of this particular circle are kind of stable commodities, major commodities that get mined. And the closer you are, in terms of the closer an element appears to that, like for example, aluminium and gallium, there is a lot of gallium developed from aluminium deposits. There are no gallium deposits out there to be found, or at least not that we know of at the moment. For zinc, for example, you've got a close association with indium, germanium, and lesser so with gallium. So in order to be able to develop those resources, we need to know in which of the existing mines do they actually occur in. And this is where we come a little bit outstuck. The JAWS code that Allison talked about, well, it doesn't report how many critical minerals are found in most of the deposits. And the reason it doesn't do that is because the critical minerals are not viewed as economically material to their operations, and therefore they don't need to report them. So we need to find a different way to be able to, I suppose, infer that, to be able to open up or at least identify the opportunity that may exist in already operating mines across Australia. So to do that, what we've done is we've teamed up with the United States Geological Survey and the Canadian Geological Survey under the Critical Minerals Mapping Initiative. There what we've done is we've pulled together our collective knowledge of the chemical compositions of ores, of deposits in our countries, of information that we've got on deposits in other countries, and we've classified them under deposit styles. So just because we want to go and mine zinc doesn't mean that all zinc deposits are made equal. There are actually a number of different processes that have occurred to concentrate zinc, and they form very specific types of deposits. We're continuing to work on this, but I'll show you how it might be used. So sticking with zinc, for example, and with germanium, what we can do is we can extract the numbers of how much germanium, which is the x-axis, the germanium normalized over zinc, occurs in 5 different styles of mineral deposits. Those are the histograms on the left-hand side. And just by the prevalence of the histograms heading out to larger numbers on the right-hand side, you can see that 2 of these styles of deposits have more germanium in them than the rest. In other words, if you're looking for a germanium source, you should be looking for those 2 styles of mineral deposits as opposed to the other ones. And within each one of them, we can then come up with relationships to not just know that germanium is associated with zinc, but to work out if you have this grade of zinc, how much germanium may you expect to have in this deposit. And using that, we can then kind of infer where larger germanium deposits may well be. And it turns out that, Australia has a very large concentration, but a lot of the stuff we don't extract. It may well be going off in the concentrates to other countries to be extracted in their particular smelters. Now, this potential for byproducts is also a significant focus of the Critical Minerals Research and Development Hub. Another focus for critical minerals for us is to team up with agencies which have expertise, particularly in downstream information. So this is CSIRO and ANSTO. And we can start to ask questions like, for example, if we know that there is only a certain type of processing technology to extract critical minerals, what type of deposits should we be looking for? Or we know that we've got these types of rocks and these types of deposits, can we find out what types of processing technologies we should be developing to unlock the critical mineral potential?
Thanks. So, and related to this, another option for potentially gathering critical minerals is to look at our mine waste. So reprocessing mine waste from active and historic mines could theoretically supply critical minerals faster and lead us with a better environmental legacy. So Geoscience Australia has been undertaking a national mine waste assessment with our collaborators from universities and state geological surveys. So the work has included mapping the location of mine waste and processing sites, analysing waste material for a range of ore deposits, and using satellite imagery to estimate the volume of mine waste storage facilities. And as part of the project, we've published the world's first Atlas of Remining Potential, which currently shows the locations, associated mineral commodities, and operational status of more than 1,400 mine waste sites across Australia, with more sites, information and capability to come as that project progresses. And sampling reports are also available, with more also coming in the next few months. Now, while reprocessing potential is an area of interest, so too is actually is understanding our actual processing capabilities and capacity for producing those critical minerals. So the slide shows that our current critical mineral and strategic material, it shows our current refineries, smelters and manufacturing facilities. And there's 33 sites around Australia covering a range of commodities, including the battery minerals, nickel, cobalt, lithium, plus other minerals like silicon and copper and aluminium. And already that charge to value add to our resources is underway. Here we've added in the 11 critical mineral and strategic material facilities that are under development, committed to or announced. Now, history shows us that not all of these projects will succeed, but many will. And that means Australia will have new processing capabilities for rare earths, graphite, and a range of cathode precursors in the foreseeable future. But this growth in downstream supply needs to be supported by upstream supply, which brings us to the final section of the talk.
So we've got 10 minutes. We've got to get through quite a bit here because this is the exciting bit, the geoscience. So how is Australia growing its critical minerals sector, including through how we at Geoscience contribute to that? So look, the primary platform for the government is the Future Made in Australia. It's an investment of $22.7 billion over 10 years, focused on net zero transition streams and economic resilience and security, with the focus areas listed here on the right-hand side, including renewable hydrogen, green metals, and yes, you guessed it, critical minerals. As the Prime Minister said, we need to aim high, be bold, and build big to match the size of the opportunity in front of us. There are a range of different measures that are in place to do this, including a 10% critical minerals tax production credit, focused on Australia taking just the next step to realise downstream value from the critical minerals sector, not necessarily getting to the very end state, which is a point of difference to other countries. I draw your attention to these last 3 bullet points. This is where Geoscience Australia contributes specifically. The Exploring for the Future program, which has just ended, the Critical Minerals Hub that I just mentioned earlier, and the Resourcing Growth Prosperity Initiative, which we'll raise in a minute. All of these are really focused to accelerate resource discovery and development. What is the number one factor that drives this? It's actually the quality of the deposit itself. So here, what you can see is years after discovery on the x-axis and the percent developed of those styles of deposits, regardless of when they were discovered. Tier 1 deposits are deposits that have a net present day value of over $1 billion. You can see that they are developed first. The next is deposits which have a net present day value of over 200 million, and so on. So the challenge really is, how do we identify a pipeline of these quality deposits to maintain industry activity within Australia? And this is something that Australia has had great success in. We've got a very strong sector, but we cannot take it for granted. In my time here, I remember being in the minerals division, and the chief used to put up this slide every year, and it was pretty depressing. We went from a high of capturing 23% of the world's market share of exploration in 1993 down to 8% in 2015. When we went and asked industry why, they said pretty much the search space has been exhausted and we're going elsewhere. So the challenge for us was, how do we identify new opportunities in Australia? And the solution was, the opportunities lie at depth. And the challenge was to uncover those particular opportunities. This is what the Exploring for the Future program significantly invested in. We acquired tens of thousands of line kilometres of airborne geophysics, tens of thousands of geochemical analyses, thousands of ground geophysical stations, tens of kilometres were drilled, and over 1,000 data sets and publications were released as part of this program. It was hugely successful and provided the platform for the next stage of investment in pre-competitive geoscience.
All right. So, and that's where the next step comes in. About resourcing Australia's prosperity, and yes, you get to hear me talking about it, not Karol this time. So, as Karol showed on the earlier slide, this is a $3.4 billion investment by the Australian government over 35 years to take us out to net zero in 2050 and beyond. It's led by Geoscience Australia, as you know, in partnership with Australian state and Northern Territory governments, and can be considered a generational investment in Australia's future prosperity. With $566 million over the first 10 years, we've been consulting extensively with government, industry, academia and service providers to inform our strategic planning and the development of our 10-year roadmap. Now, the initiative, as you've all seen this triangle, comprises 4 interrelated components, as shown, and I'll use the next 5 slides to just quickly show you some examples of the work we're doing and how it relates to critical minerals. So the first component is compilation, collection, interpretation of those foundational national scale geophysical, geochemical and geological data sets that advance our understanding of our continent. And the example on the slide shows the National Airborne Electromagnetic Project, which is progressively covering Australia with 20-kilometre line spacing. The survey enables us to image the electrical conductivity of the Earth down to depths of 300 to 500 metres, which supports mineral energy groundwater mapping, and that includes understanding more about those search spaces within and beneath the cover for critical minerals. The second component is the National Resources Assessments, and we're doing these for critical minerals and strategic materials, groundwater, geological storage of hydrogen and carbon dioxide, and seabed suitability for offshore renewable energy infrastructure. Now, throughout our consultation with industry, the critical minerals of greatest interest are copper, rare earths, cobalt, nickel and lithium, and we'll be carrying out mineral potential assessments of all 36 of Australia's critical minerals and strategic materials during the initiative. Deep dives are the third component, and are detailed multi-commodity assessments of regions with unrealised resource potential, including for those critical minerals. And under the initiative, we'll complete 4 of these in the first 10 years and are committed to 12 over the entire 35 years. Now, just as important as what we do is how we go about it. And this is the fourth component of the initiative, which recognises the vital importance of our data delivery and engagement with stakeholders and partners. And the photo you see is a powerful example of collaboration with First Nations people in action. It captures a moment from Geoscience Australia's recent work with the Lake Eyre Basin Ranges, and it provides where we're providing training and teaching how to describe soil profiles, and that knowledge is now being integrated into broader land, water and ecosystem management practices on country. And so with this people-first approach, we're also committed to advancing how we communicate and deliver our geoscience. And many of our stakeholders, they're not subject matter experts, and they don't necessarily find useful the tools and platforms that we technical experts, think are amazing. And so we've created Geo Insight as a way to show rapid region-based information about water, minerals and energy in an award-winning, user-centred interactive platform. And we're going to continue expanding its capabilities and coverages. And we'll also look at innovative ways to improve access to geoscience data, including through our existing data discovery portal and making our data AI ready. We all know it's coming. Well, it's here. So I hope I've been able to show you some of the ways in which the Australian government is responding to that urgent need to develop our critical minerals sector through government geoscience. But why have they backed this horse in particular? So I'm going to hand you back to Karol now to tell you a 5-minute story.
All right. Thanks. So why have they backed it? And what type of impacts might we expect to come from this future investment? So what we do is, following data releases, we actually go and we talk to companies, to exploration companies, and see, is the work that we're doing of any use to them? We've got a person that's keeping an eye out on the tenement map of Australia, and when a new tenement goes up or a new merger happens or significant new investment, they give them a call and say, hey, notice this has happened. What information led you to do this? And a lot of the times, it is the information that is provided out of Geoscience Australia in collaboration with our states and territory partners. It's amazing that since about 2016-17, over 174 companies have picked up over 1,000 tenements over almost 6,000 square kilometres across Australia. That's a huge, huge area to be exploring in now, and it actually has led to the discovery of 6 resources. 4 of them actually rare earth elements, and the others copper and gold. Now that's what's happening in terms of spatially, in terms of exploration. We can also see this in a reversal of that declining trend that I referred to before. So here you can see that while exploration share has left maybe areas of greater sovereign risk and gone to places like Australia, Canada, US, and so on, I'll put it to you that you would not go back to explore an area where you thought there was nothing left to be found. So I think we have been successful in identifying a new exploration search space. What are people exploring for? Well, a lot of the investment does go into gold in Australia, especially at the current gold prices. But notice there has been a huge change recently in terms of this category of other metals. That's the critical minerals. Unfortunately, we don't have additional granularity in terms of exactly which minerals that expenditure is being made on, but the point is that it's either the second or the third largest now over the last 2 years in terms of mineral exploration expenditure. So the critical minerals pivot in Australia is truly started. So how successful is this? And here's an assessment. What we're doing at the moment is we're trying to assess what is the exploration discovery story of the world's Tier 1 and Tier 2 deposits. We're going back to doing this from 1990, but here's a snapshot since 2017, because that's the bit that we've achieved so far. There were 41 of these discoveries globally, and only 10 of these, and 10 of these were in Australia. That's a very large chunk of the pie. Out of those 10, 7 were underpinned by pre-competitive geoscience provided by ourselves or the states and territory surveys. If we have a look in detail in terms of what they are, here's the list of all the ones that we know that have been underpinned by pre-competitive geoscience over that time around the world, these Tier 1 and Tier 2 discoveries, so the ones that get developed fastest. There's a few points to kind of make here. The names of the deposits in green are in greenfield areas. Most of Australian ones are in greenfield areas. That's where the largest deposits get found first. Second of all, have a look at the depth column. There is one at 0. So for critical minerals, the surface has re-emerged as an exploration search space. We weren't looking for that back in 2015, but all the other ones are deeper than all the others discovered around the world. In other words, we have succeeded in unlocking the undercover search space and demonstrating the opportunities there. And the third thing I want you to take away from this, is that there is a diversity of different mineral systems. We're not just looking for one style of deposits. And last, if you look at which pre-competitive geoscience actually contributed to it, you notice there is no silver bullet. That is why our programs have such a diversity of data and analysis that we collect and we provide, because there is no silver bullet to this, and it all matters in an integrated manner. Now, we can do this on a case-by-case basis like this, but we also stepped out and said, what difference does this make to the entire economy within Australia? So through surveys of companies, in terms of do you use this information or not, we're able to identify about 80% of companies are using this information to support their exploration, and this is not including coal and iron ore. We didn't ask those companies these questions. Deloitte Access Economics did a study on this, and what they realised is from an investment of $71 million in data production, there is a further $5.5 billion of value-added activity in the activity that was supported by that. But that's not the end goal. Exploration, well, it's kind of a nuisance unless it actually leads to the discovery and development of the thing that we're looking after. So the thing that we're actually interested in supporting is the resource extraction value, which is much, much larger. And it's about 3.5% of GDP. So with that, I'm going to stop because we're over time. And apologies for that.
All right, so just to finalise, that brings us to the end of the presentation. We've shared with you our expertise on critical minerals and why they matter. We've talked about the history and geopolitics involved and provided an Australian perspective to help make sense of not just the headlines, but also Australia's opportunities and barriers for leveraging its resources endowment to meet that demand for critical mineral supply chains. And hopefully, we've been able to instil in you an appreciation for the important role that we play as government geoscientists in ensuring that Australia can find the resources needed to create new and diversified critical mineral supply chains. We're happy to take questions if there are any, but we're over time. But we'd also encourage everybody to check out the AJES Special Edition on critical minerals, which has not just our paper, but a number from Geoscience Australia, amazing papers. So thank you, everybody.
All right, thank you, Allison and Karol. I am sure you were all captivated and didn't realise we went over. For those of you in Geoscience Australia, you know where to find Allison and Karol. So if you do have any burning questions, you go find them. Anyone online who isn't from Geoscience Australia and has a question, please pop it in the chat and we'll see what we can do to get back to you on it. Now, once again, just quickly thank me. Once again, please join me in thanking the team for that fantastic presentation. Look, and before I close, I just want to advise we're having a break from our public talks over Easter and the school holidays, Our next public talk will be on Wednesday, the 30th of April. We're going to hear from Verity Normington and our education and outreach team, who are going to share with you some ideas on how to celebrate Earth Science Week as we kick off the planning for this event. So please join us 11 a.m. on Wednesday, 30th of April, and I hope to see you at same bat time and bat channel. Registrations are available at ga.gov.au/news/public talks. Thank you all for staying with us, and thank you for a great presentation to Karol and Allison. I'm closing it.